Okay, today's lecture is about differentiation in the context of measure theory. So you all know classically what that means. It's the link between the derivative and the integral, which is embodied in the fundamental theorem of calculus. So if I have a function and has a derivative, and you can integrate it, then the integral from a to b of f prime of x is fb minus f of a. Okay, so that's the genius of Leibniz and Newton, linking the tangent problem of finding the derivative and the squaring problem of finding the area under the curve. Now we want to look at this in the setting we have been developing, so more generally. So we can ask the question, what kind of function have this property? Now we have an integral which is more general than the Riemann integrals. We have the Lebesgue integral. So probably we can actually generalize this to more function. And we already know that actually we should have that the measure that you construct from f, right? It's constructed on interval a and b, so this is essentially the measure of the interval a and b. So this says essentially that the measure you constructed from f is absolutely continuous with respect to the Lebesgue integral. So what does it mean for f itself? That it can be written as an integral. We'll see that there's a property called absolute continuity, which is where the term comes from for measure. So if f is absolutely continuous, I can actually write f of b minus f of a as the integral of some derivative, right? So it says in particular that the measure that you constructed from f is absolutely continuous with respect to Lebesgue measures, so that's why we use the same terminology. Okay, so that's what we're going to do today, the link between the derivative and the integral. So the main tool is going to be something that we're going to prove in more generality next lecture. We're going to use that shamelessly. It's the Lebesgue differentiation theorem. So if you look at what I have here, okay, I can actually, if I divide by b minus a and think of b minus a as small, this can be written essentially as the average of the integral. Now I wrote small f for the f prime, so it's the average of the integral. And in what cases does that converge to f of x? So if you think about this, it's very similar to the setting I have here, except in terms of dividing by b minus a and then taking the limit. So there's a general result called Lebesgue differentiation theorem that says this holds in very big generality, that if you have f, which is an integrable function locally, L1 loc, I'll see what this means, then this averaging over any ball, so this holds in RD, we're going to prove that in RD. Then if I average f in a ball, by averaging, take the integral with respect to the Lebesgue measure, so here, when I write dy, right, it means Lebesgue measure. It's just, sometimes we use the classical notation, and I divide by the measure of that set, so it's really like an average on that set. Then when r tends to 0, r is the radius of the ball, this goes to f of x almost everywhere, so this is m almost everywhere with respect to Lebesgue measure. Okay, so what is L1 loc? Is what you think it is. That is, it's a function that if I integrate over any compact set, it's finite. Okay, so that's much larger than L1 of RD. Okay, and always with respect to the Lebesgue measure. All right, so Okay, it turns out that we're going to prove something more general. So that is this implies that. So if you send f of x on the other side, f of x I can enter into the integral and then take the absolute value. Okay, what we're going to prove is that actually when I take the limit of the absolute value of the difference, then the measure of that set where this is not equal to 0 is actually 0 when f is in L1 log. Okay? So this set actually, as the name is the Lebesgue set of f, and it has information about the regularity of f. So essentially you can read that as saying that if you're in L1 log, you're quite regular because the set where this is not equal to 0 is 0. Alright, this is a bit the introduction to the subject. Now I'm going to jump to the results related to the fundamental theorem of calculus. Okay, so let's start with a simple consequence of the Lebesgue differentiation theorem. So let's read the statement together. So now I work in R. Okay, so fundamental theorem calculus is in R. So I have new irregular. Okay, remember what regularity means: sigma finite sign measure on Borel sets of R. Then if I take the ratio between u of Brx and m of Brx, and Brx only a ball of radius r centered at x, so it's really just that interval x minus r, x plus r. Then when I take the limit r to 0, so I shrink that box, then this is equal to f of x, m almost everywhere. Now what is f of x? That's quite important. So nu, we know from last lecture, right, that I can decompose any sigma finite sign measure. Sigma finite was important for Radon-Nikodym theorem in terms of its singular part that I don't see here, it's 0, and the absolutely continuous part that I see. Alright? So that's the statement. And we're going to use that statement to actually get the fundamental theorem of calculus. We're almost there. Alright, so let's look at the proof together. Now, if you look at the Lebesgue differentiation theorem, it says that if I take the measure which is the integral of f dm, this converges to f of x. That's m almost everywhere, right? So that's what the Lebesgue differentiation theorem says. So really, what I have to do is only look at the singular part. So that's the first reduction. Okay, so here you can always write nu as the sum of these two, and this gives you this f of x by the Lebesgue differentiation theorem. So really, I only have to show that. Now here's another reduction. So since nu s is singular, mutually singular with respect to m, we know that there's a decomposition in E and E complement such that m of E complement as measure 0 and nu s of E as measure 0 as well. Okay, so we can actually restrict the proof to x that belongs to E. And why is that? Is because, and that's not clear if you don't think about it, it's because that's m almost everywhere, right? So I don't care about E complement because it has measure 0. So this statement on E complement has measure 0, so has no content. All right, so we can restrict to x in E, all right? Now, the idea is you shrink that ball, right? So you take a ball that's centered at E and you shrink that ball, okay? Now that ball, you would like that at some points all contained in E. That would be great because nu s of E is equal to 0, but you don't know that because E might not be open. So you do the next best thing and you use the regularity. Okay? So that's why you need regularity. So I have my set E. Okay? And the measure of E is the infimum of, that's regularity, the measure of open set O that contains E. Okay? So you take an open set O, which is close to E in measure. Okay? Now you're going to say, okay, but that's for nu is regular, but nu s is also regular because nu is FDM plus nu s, and this guy is regular because it's a Lebesgue still just measure. Think about it. All right? So you're good. So so you work with that open set. Okay? So we can find open set. For any epsilon, we can find O such that O contains E and nu of O as small measure. Okay? Looking at the positive total variation of nu. All right, so I want to show that this is small. And so here, I'm sorry, should be nu s. There's a lot of typos, but I'm trying to correct as we go. Okay, so we define the set AK, which this ratio, when I take the limit, is bigger than 1 over k. All right. Okay. Now we show that the measure of AK is 0 for all k, and therefore, just by taking the limit, note that these sets are increasing, so you can take the limit of AK. It's gonna give you the measure where it's strictly bigger than 0, and we show that it's 0, so that proves it. All right. So let's show that. So so by definition, I take an x in AK. So by this definition, I take R small enough might depend on x, so that M. So just looking at this inequality, you get that. Now here comes the important part. So O is open. So if x is in AK, it's also included in O because x is in E. We can take Rx small enough so that the ball lies completely in O. Okay, so that's important. And then you take the union of all those balls. Okay, and now so it looks a picture like that. That's my AK. I have all these yellow balls. Now you would like to actually take a countable covering, disjoint, a subcovering, so that you actually don't lose too much. It's not an exact covering, but you don't lose too much of AK. And there's a nice result called Vitaly's covering lemma. I won't do we're going to need that for the Lebesgue differentiation theorem, so I'll go back to that on Friday. But let's take it into account, let's take it for granted that you can find disjoint balls BJ, okay, those are in green, so that if I look at the measure of these disjoint balls, it's bigger than 1/3, okay, with some MAK, so I don't lose much in measure from my set AK. And once you have that, you just do the chain of inequality, okay, that's this inequality. Then I use the fact that disjoint, okay, measure is additive. Then I use this inequality. Then there's a sum missing here, okay. I use additivity again, okay. And the sum of BJ is smaller than O. I might lose some, okay. O is included, contains the union of the BJ. And I know that nu of SO is small. That was my beginning part. And epsilon is arbitrary, so I think M squared goes to 0 and I'm done. All right? So nice little result, Vitaly's covering lemma. We're going to see that a bit later. Okay? So great. So we have this result that the only thing you see is the absolutely continuous part of the measure. All right. So let's use that now. So other ingredient missing, I want some derivative, and I'm only averaging on balls here. But this result holds for any set ER, not only balls, but any set ER that shrinks nicely, as Fallen says. Okay, so what does that mean is it's a family of set that are contained in the ball for every R, and you don't lose too much in measure. Okay, so the measure of ER is bigger than some constant BRX, even though it's contained in it. Okay, and it's easy to see that actually the same theorem holds with BR replaced by ER. Okay, so I do the little reasoning there. Okay, and now let's apply that. Okay, so that's the essentially the fundamental theorem of calculus revisited. So if I take f of bounded variation, I know that I can construct a measure from it. Then I know that f prime exists, m almost everywhere. It has a derivative. This derivative is in L1. Moreover, if the measure I construct is absolutely continuous, then actually I can write that f as the integral of f prime. If I'm singular, then f prime of x equal to 0 m almost everywhere. Okay? And the second case, remember the Cantor function. We saw that example in class. That is, the Cantor function is a continuous function, and it's increasing, so it has bounded variation, so I can construct a measure, but it's mutually singular with respect to the Lebesgue measure. So in particular, that we know that f prime is equal to 0 m almost everywhere. Okay, by this result. So, all right. Okay, so this is an easy consequence now of the Begg differentiation theorem. Why? Well, I just applied the result to the set ER, x, which is equal to x plus r. So this family of sets shrinks nicely. I have these two properties. Okay? So what happens is the measure of ER is just f of x plus r minus f of x by the definition of the construction of the measure we have. And of course, the measure of that set is simply r. So I recover the definition of the derivative. Then I take the limit r tends to 0, and what I get is this, and by the last theorem, this is just f of x m almost everywhere. Okay? So we have that the derivative exists, and the derivative is given by the Radon-Nikodym derivative. Okay, so this is actually, I should say, f of prime. So the derivative exists. This is classical definition of the derivative, and it's equal to the Radon-Nikodym derivative that we already saw. Okay. Okay. Good. You can do the same thing with the left derivative to have the derivative. So actually this is f prime, actually the right derivative. But then the same argument gives you the left derivative, so the derivative exists. All right. So about the last two claims. So if you're actually mutually singular, so the Radon-Nikodym derivative is 0, you get the f prime is equal to 0. And for the other thing, so if you're absolutely continuous, then you can write f of x as the integral of the Radon-Nikodym derivative, which is f prime. Okay, so the correspondence is really between the classical derivative and the Radon-Nikodym derivative. All right. Okay. So I think I'm going to stop here, and I'm going to do the, so what's left in the lecture is to actually to look at the condition. So when do we actually have that the measure construct is absolutely continuous with respect to M, and that's the property of absolute continuity of the function. Okay, and so it shows that if you're absolutely continuous with respect to M, the function f should be absolutely continuous, and then in that case, the derivative of this absolutely continuous function exists M almost everywhere. So I'm not sure about this assumption here of f prime belongs to L1. This is probably only if you get a finite measure. So I should take that with a grain of salt. All right, okay, thank you.